All right, let's get started. Okay. Cool. I'll first put this up on the board. There's quite a few GIFs up here. I'll talk about them one at a time because I don't want to overwhelm you guys. But I think the GIFs are really useful to help you kind of see what's going on and understanding the properties. So, first type of solid that we are talking about are the metals. I figured that's the most familiar that you guys have interacted with, and I think logically it's easiest to understand. As you guys were doing in your pre-learning, you would have read stuff about the properties of metals, and yesterday when you guys went to go pick up a stick and compare that stick to a paperclip, we noticed some certain properties that those metals had as well, such as the shininess, that you could bend it and change its shape, that it was really hard to break it apart. With those properties, it's one thing to be able to identify what they are. It's another thing to be able to explain why they have those properties. That's where we're getting towards the merit level answers. The way you explain it is through the particle makeup and the bond that is present. So those two things will factor into explaining why they have those properties. So first thing we're going to talk about then is the just a generalized, I just want to spotlight this, the generalized component of what a metal is. So metals are consistent of, sorry, let me backtrack. So when you guys filled in that table of the identification, you wrote down that metals, the particles that make up metals are atoms, which is true. What we're looking at here are atoms. With those atoms, however, metals have this unique feature, and that is that their electrons are delocalized. So what we have is the positive nucleus, and when we think about atomic structure, that is normal and consistent between all atoms. In that nucleus, you have the protons and the neutrons. Neutrons have no charge, protons are positive. So that's why we see these kind of big pieces here. Then when we go outside the atom, you're going to have those electrons that are floating around, and those are negatively charged. Remember, electrons are really, really small, and their mass is basically insignificant to the atom. In metals, their electrons aren't tied to one specific atom or say one specific nucleus. So in other substances, those electrons are very heavily tied to that nucleus. They'll stay around it. I won't use the word orbit because that's technically not the correct word, but you'll learn that in level 3. Anyway, the electrons in this case are delocalized, so they can buddy up with any of the other positive nuclei. They can move around. So this GIF doesn't show it really well. I haven't found one that I really, really liked. But basically, this electron here that I'm pointing at, and I'll actually get it with my mouse so you guys have it on the recording as well. Hopefully my mouse actually shows up on here. There we go. Let's say this electron that we're thinking about right here, it could be attracted to this positive nucleus, but it could also be attracted to this one as well. So they can move around this whole sea of the positive nuclei and just kind of, they're not set to any one location. So that's going to give metals a lot of unique properties. So first unique property that it's going to get because of these delocalized electrons is the shininess. So that's why metals are shiny. It's the delocalized electrons. If you want, you're welcome to write that down. I'm not going to write it down because they don't often ask that question on the exam. We'll talk about some of the other questions they ask. One of the questions they do commonly ask about the metals is their conductivity. So metals can conduct electricity. That's why we use it for wires. To be able to conduct electricity, you need a mobile charged particle or free-moving charged particle. So I will write that down because that's going to be an important factor when we talk about our properties. So lots of different properties they talk about. Electrical conductivity is a common one they do ask questions on. So let's write some notes on that. So first thing to keep in mind, to be electrically conductive, you need a free-moving charged particle. So when I say mobile, I'm talking about something that's free to move. Charged particle. And the reason why I'm using the word charged particle is that this here is a very generalized term. It's an umbrella term. So there's lots of charged particles. There's the electrons, there's anions, there's cations. So just be mindful when we talk about a charged particle, we're talking about electrons. We're also talking about ions. I'm sorry that's flickering. I'm trying to see why is it doing that. Okay, stop. See if I can also find you guys a GIF of what it looks like. Oh, no, not on Spotify. You guys are seeing what I listen to. All right. So this is an important thing for me to talk about with the electrical conductivity and explain that you need a free mobile charged particle. Lots of different types of solids. Lots of different types of solids are going to be able to conduct electricity. It's not unique just to metals. We'll learn that there's some other ones that can do it too, and we'll learn the reasons why and the conditions they need to have in order for that to happen. For metals, they can conduct electricity because they have a delocalized electron. So that's the reasoning behind that one. Let me grab another color pen. Wanted green, so it's green and green. All right. So for metals, they are electrically conductive. Electrically. Oh, I can't spell today. There we go. Conductive. Because they have delocalized electrons. So that delocalized electron is basically meaning the electron isn't tied to one particular positive nuclei. Just like in that picture that you saw in that GIF. Just watching the time. Shoot, maybe need more than. It's okay. If not, we'll just pick this up on Monday, and that's my fault. I don't think I spelled electrically right either. I don't think I spelled electrically right. Oh my God, I did not spell that right. Trust me, let's spell it right. C-A-L-L. Why? Sorry, I misspelled it. I try to fix it if I can do it. All right. Huh? I'm sorry. If you think I spelled it wrong, just write the way it's supposed to be spelled, and hopefully I catch it. Or tell me that it's wrong. I spelled it wrong. I'm sorry. All right. Can I keep going?
Wait, what's the word of the particle?
Positive. So this is my shorthand. You're going to learn some of my shorthand. That means positive.
What is that? CVE?
Yeah, positive. So this bit positive. Nuclei. So the nuclei is it's referring to a single, nuclei are those positive nucleuses. So my nuclei, plural for nucleus. Yeah. And then valence electrons that are delocalized. So they basically can travel any which direction they want. Like that. I pick out GIFs because I think GIFs help kind of visualize what's going on. All right, keep going. Okay. So I just want to point out to you guys, so right now in this GIF, there is an electrical current running through it, so these delocalized electrons are just moving randomly. But the moment that I put an electrical current through it, I then get the electrons to travel in a set direction. So that's just something to kind of keep in mind when we are thinking about electricity and their conductivity. Are we okay with that one so far? Okay, cool. I'll move on. I'm just watching the time. We might have to continue the notes on Monday. That's my bad. I did not budget enough time for it. Okay. Some other things that are unique to metals that you wouldn't find in other types of solids is something called malleability and ductility. Malleability is referring to the ability to smash something and it changes its shape. It doesn't break apart. And you guys saw that with the paper clip. You could bend it out of its original shape and it wouldn't just snap all of a sudden. Whereas with the twig, the moment you tried to apply any pressure to it, it just broke. So that's what we're referring to when we're referring to malleability. Ductility is similar to malleability. Ductility is referring to if I can pull it into a thinner wire. So that's how we're able to get thinner and thinner wires. So what we're thinking about again is that reason why. So the reason why has to do with the fact, let me open up this skiff instead. Spotlight it. There we go. Okay. Load GIF. There we go. All right. So what you see here is you see that sea of electrons, and that black block is acting as a form of pressure, of force, and it's changing the shape of that metal. Now that metal is not snapping in half. It's going to be able to take on that shape because, again, that unidirectional bonding. So since there isn't that directional bonding and that these bonds, these metallic bonds between the electrons and the positive nuclei can reform, it can then change shape. So that's what we're looking at there. Same with this skiff over here. I won't write this down now. I'll write it down on Monday. I'm sorry, I did not budget our time properly, but that's good for you. So we see here in this GIF, a pressure has been applied, and again, it's able to accept that change and change shape without breaking because of that unidirectional bonding. So there's no set 3D structure in that case. So that's why it has that property. Questions about that? I'll write it down on Monday. I'm trying to think what else I have. Actually, maybe I'll start writing it down. We'll see what the bell's supposed to go soon, isn't it? Thank you. We do have enough time for the notes. I'll keep going. My bad. Let me just get one of these sheets. I want to make sure I spell the words properly. All right. Thank you, everybody. I look like a fool. Waited really long to ask me that question, to tell me that, didn't you? All right. So, malleable, you guys have the definition for that one. So malleable, we're talking about can I change shape? Not on the, not a good day for me. Right, malleable means it can change shape with force. So ability to change shape without breaking. And then ductile is similar to malleable, but it's specific to then drawing it out into thin wires. Similar meaning. Similar meaning. We're just talking about being able to pull it into a wire. Changing the shape by pulling it into a wire. Cool. And I'll leave that up for you guys to write down. I just want to show you guys an example of what ductile is. I just want to show you guys what ductile means, just because I'm mindful, like malleable is pretty obvious. You hit it with a hammer. Ductile is you're pulling a wire and you're making it narrower and narrower. So I actually did this when I was in high school because I did a jewelry making class. And what they had as a bit of equipment is they had these little metal block with different size holes. And what you would do is you would take the wire that you're trying to make into a thinner wire, and you would pull it through this apparatus, and it would reshape the wire, and so it would become out thinner on the other side. So what I would basically be doing was filing down the metal, so that way the metal could actually fit through the hole, And then I would grab some pliers and I would wax the metal so that way it would go through the tool smoothly. I would pull the wire through and I would make a thick piece of wire into a much thinner piece of wire. You can't jump from like really thick to really thin. You have to go through each step and slowly make it into a thinner wire. But that's what we're referring to when we say ductile. So I just want to show you what that means. It's pretty cool. I'll bring in I still have some of the jewelry I made in that class. I'll bring it in to show you guys, and I'll use it as a means to teach you about different properties. But I'm going to wait until we talk about the other types of solids beforehand, so it all makes sense. All right, so that's what ductile is meaning. The reason why this guy is ductile has to do with the fact that this is non-directional bonding. So it means it doesn't have a set 3D lattice. So this here is possible because metals have non-directional bonding. AKA no set 3D lattice. When we're talking about a lattice, we're just talking about a set structure. And what that also means then when we're looking at this image here, we have these metallic bonds, but the metallic bond for this electron is between this electron and this positive nuclei. It'll also be here as well. Like all these guys are just, it's non-directional. So they just all kind of bond. And then if I apply a force to it, I will break this bond, but it will make a new bond with a different positive nuclei. So that's why that shape is allowed to change. And like I said, you can see it a lot in the GIFs. So I'll go back to the gift as well so you guys can see that. But I'll give you a chance to write that down before I do that. Questions so far? Because you guys are going to learn all my shorthands. You had me last year, Indira. You should know what my shorthands are. Because. Don't do that on the exam, though, because they're not going to be happy if you're shorthanding. I'm a teacher. I'm trying to get you guys this information fast. The other one you're going to see me use is the 3 dots for therefore.
What the?
That's a math thing.
Is this all or not?
These are all notes.
And it's recording it.
And I'm recording it, and I'll scan this.
Yeah, because I like going back to it.
I know. That's why I do it. All right. Keep going. Okay. So just want to show you the gifts again, just to kind of reinforce what we were talking about. This one in particular is a good one because I think it does a better job. Spotlight it. There you go. So, like I said, non-directional bonding, and then I apply some force to it, and then it just starts making new bonds with the other positive nuclei. So, it doesn't really matter. This one here is actually a really cool example because this is not a pure metal, like one element. It's actually an alloy. So you can see that you have the positive nuclei and then you have something else in there. That something else that's in there could be a different metal. It could also be a different element altogether. And what that does is it changes the property of that metal and might make it harder or things like that. So a good example would be gold and silver. So we wear a lot of gold and silver. You'll notice if you look on your silver, most of those silver should say 92.5. So that means it's 92.5% silver. Yeah? The other percentage of the silver, say for example my ring here, is usually copper. And the reason why they mix some of the copper in with some of the silver is to give it more hardness to it. It helps resist its ability to accept that change of movement when you add that pressure. So then my ring doesn't change shape when I slam my hand down on the table. The other example of that would be gold. So you know how gold has different carats? So there's 24 karat gold, and that's the best one. That has the highest ratio of gold mixed in with probably copper again. So 24 karat gold, the reason why we know it's 24 karat gold, and you'll see this in old Western movies, is that they will bite into the gold coins to check if it's soft. So if it's a pure gold metal, it's going to be really soft and you can bite it and you can leave teeth marks. In fact, I've had this necklace since I was 6. My mom gave it to me. I've worn it since then. It's really precious to me. you can see there's little teeth marks on here because I've had this since I was 6, and when I was a kid, I used to chew on it. So that's 24 karat gold. That's really soft. If you have a cheaper gold, it's going to affect its luster. It's not going to be as shiny. It might not be as vibrantly gold. It also won't be as soft. So it's a good way to kind of check if things are legit or not. Cool. All right, so that one's malleable. That one often comes up on the exam because that one is unique to metals. The other types of solids do not have that property. So very commonly they ask that one. There's 2 other ones that do come up. I'll write them down. They're not usually asked in huge amount of depth, but just in case it does come back, I want to make sure you guys know the reasons why. So one that does come up is going to be high melting point, high boiling point. When it comes to ranking them, silver is probably somewhere along the middle, if not kind of second to last. Or sorry, not silver. Metals are kind of second to last or mid of the range. They do have a high melting point, but it's not as high as some of the other solids we will look at. But they'll most likely be solids at room temperature. The only exception to that is which element? Which element is a liquid at room temperature? Do you know? Mercury. So mercury is a liquid at room temperature. I'll see if I can find some. We haven't unpacked the lab, so I don't know if we still have it. But mercury is a liquid at room temperature. So high melting and high boiling point, that has to do with the fact of strong metallic bonds. So now we're talking about the metallic bonds and what that influences. So we have strong metallic bonds. So if you guys remember when we were filling in that table, metallic bonds are the bonds for the metals. Those strong metallic bonds are what's going to cause something to be high melting point, high boiling point. Not even going to talk about boiling point because it's usually not coming up. Sorry, melting point. The other thing that those strong metallic bonds will do is that they will make them insoluble in water. So these will not dissolve, which is good. I don't want to wash my hands and have my ring disappear. And we'll go into more detail about solubility in its own separate lesson. I just don't want to dive into it too far at this point because it'll make more sense after I've talked about molecules. And I think that's basically everything that you need to worry about with their properties. Yes. Cool. All right, questions, concerns, comments? This actually worked out, which is like timing-wise. Okay. So, let me tell you guys now that you guys have done your notes. So, what you guys can do is you can continue working on those 82 to 87 pages. Skip the questions that I've mentioned because they're starting to do that compare and contrast, and we haven't actually looked at another type of solid to do that compare and contrast. The other thing now at this point that you've had your notes, you can do 90 to 92. Something to keep in mind is that I don't need you to finish all these pages right now. You can save some for later in the year when you're revising for the exam, but it's a good idea to still do some of those pages to double check your understanding. All right, there you go.